Okay, let's introduce friction. So friction is going to be that force that resists sliding. Okay, so we're going to break it into two types. There's a static situation where it's resisting the sliding, but there is no sliding yet. Okay, this would be if you put something on an incline and it doesn't slide down, so it just sits there. Friction is opposing it from sliding down, because if there wasn't friction, it would slide down. So that would be a static situation. Now, the one that people get confused about with static is it says no sliding. It doesn't say no motion. Okay? So whenever cars are driving on the road, as long as they're not like drifting, they are actually in static friction. Those wheels are not sliding on the road, so it has static friction. The other type we're going to look at is kinetic, where there is sliding. The two surfaces are sliding past one another. So if we run into a situation of static friction, that force of friction starts out at 0 and it can get as big as it needs to get until it reaches a maximum value of mu sub s. This is the coefficient of friction. This is telling me what are the two surfaces like that are trying to slide past one another. Are they rough? Are they smooth? Is there a lot of resistance between them? What's the surfaces like? And this is an experimental value we find where mu is going to be a number typically between 0 and 1. And it doesn't actually have any units because it's basically a ratio of the force of friction and the normal force. And so we have a static version. We also have a kinetic version. And we're going to look at what the differences are there in a little bit. So with that, we have this range from 0 to mu sub s times the normal force. And again, normal force, we can find that by drawing a free body diagram and solving in the y direction. Meaning we have a range for our static. Our kinetic, however, if it's sliding, there is one force of friction. Doesn't matter if it's sliding fast, slow, sideways, up, down. We just have a constant value of mu sub k times the normal force. Again, we can find that normal force with a free body diagram. And the thing to remember when we're doing friction, especially kinetic friction, substitute, substitute, substitute. We're just going to substitute in for force of friction, mu times normal force, then we'll find normal force, substitute in for that, and we'll go through it. So let's go ahead and take a look at an example of this in action. All right, we're going to take a look at how static and kinetic friction work. So what I have here is I have a spring scale that I attach to this block, and I'm going to pull this block across this table. And I want to watch what happens to that force of friction as I start pulling. So right now it's not moving. That means there's a balance in my forces. So the applied force has to equal the frictional force. So what's my applied force? 0. So guess what the frictional force is? 0. And so if I start to pull a little bit, maybe I pull with 2 newtons of force, the frictional force matches that. Again, we have that equilibrium situation over here. I start to pull a little more, maybe I pull with 4 newtons. Frictional force gets bigger. So that static friction, you can see, is a variable. It has a range of values. But eventually, if I pull hard enough, that static friction gives way and it starts to move. Now you notice it's moving at a constant velocity. That means that the frictional force and the applied force match. And you'll see that that frictional force was only at 6. Well, when it was static, it went way up to 8. And so we see that static friction, even though it's a range, it goes up. And then once we hit that maximum value, the block releases, it starts moving. Now we have kinetic friction. It drops that force back down. So let's go ahead and graph that on the board. All right, now that we saw that example, let's go ahead and graph what that might look like on a graph. So here I have force of friction. So what was the frictional force and versus my applied force that I might pull with? And so I started out with 0 applied force and friction was 0. It didn't need to apply any force. And as I pulled a little bit more, the force of friction increased. And it increased until we reached that maximum static friction, mu sub s times normal force. And as soon as you pass that maximum force of static friction, it starts to move, and that force of friction drops, and then it just maintains. That doesn't matter how hard I'm pulling after that, that force of friction stays a constant mu sub k times normal force. So you see as I apply a different force, here for the static situation, the force of friction varies. But once I get it moving, once we're in this kinetic range over here, it stays a constant value the whole time. That is a flat line on out there. Okay? So again, here is my range where I have static. Here is the range where I have kinetic. All right. So let's go ahead and let's talk a little bit more about why is there this difference? Why do static and kinetic friction behave differently? Okay. So one way to think about it is to think down to that molecular level. Think about, okay, those surfaces aren't actually smooth. They're a little rough. Okay. And you can imagine that if you give them some time, there's going to be some intermolecular forces that are going to oppose and pull, and eventually those rough surfaces might kind of meld together a little bit. But as soon as you start pulling them, they come out. But it takes a little extra to pull them out of that melded state. Okay? And once you get them out, you're moving them past each other so fast, because we're thinking the molecular level now, that they don't get a chance to fall back into those grooves. They just kind of go across the top. You could think about like if you hit a pothole in the road going slow, you would land in that pothole and it would be pretty tough to maybe get out if it was deep. But if you hit that pothole going like 100 miles an hour, your tire would barely fall into that hole in the time it had to go over that hole. And so you can kind of think about that in static friction is if you give it time to fall into that pothole, it's hard to get out. But if you don't give it time to fall in, it's not as hard to get out because you don't actually fall all the way in.